All right, welcome to The Explainer. Today, we're diving deep into a paper that honestly changed the game for generative models. We're talking about the 2022 paper from Peebles and Shi, the one that introduced the Diffusion Transformer, or DiT. This wasn't just another paper. It fundamentally challenged how everyone was building diffusion models. And yeah, the scaling laws they figured out, they paved the way for giants like Sora. So let's get into it. So here's how we're going to break it down. First, we'll look at the U-Net anomaly, basically why things needed a shakeup. Then we'll get into the nuts and bolts of designing DITs. After that, a really tricky piece of the puzzle, the conditioning conundrum. Then the big takeaway, G-flops, not parameters. And finally, we'll see how they crowned a new state-of-the-art model. Let's go.
Okay, so let's set the scene here. Think back to around 2022. The transformer architecture was just taking over everything. It was this massive unification force in AI, NLP, vision, you name it. Transformers were becoming the go-to. But there was this one really important area that was just stubbornly holding out. And that holdout was diffusion models. As the authors themselves put it, you had these incredible advances in image generation, all being driven by diffusion models. But every single one of them was using a convolutional U-Net as its backbone. It was just the de facto choice. With all its convolutional layers, skip connections, it was just accepted wisdom that this was the way to do it. Nobody was really questioning it. So that's the core question this paper asks. Was there something magical about the U-Net? Was its convolutional inductive bias, its built-in knowledge about pixels being next to each other, was that essential for making diffusion models work? Or was it just the way things had always been done, an old habit just waiting for a more general, more scalable architecture to come along and blow it out of the water? All right, so let's get into the solution. Let's see exactly how they went about swapping out that U-Net and dropping in a transformer to create the DiT. First things first, they're not operating on raw pixels. That'd be crazy computationally expensive. Instead, they work inside the latent diffusion model framework. So step one, you take your image and run it through a VAE encoder. This squishes it down into a much smaller latent representation. Think of a 256 by 256 image becoming, say, a 32 by 32 latent with 4 channels. That's a huge reduction in the spatial dimensions. And that's the thing they work with. This smaller latent gets chopped up into patches, and those patches get fed into the transformer, which does the heavy lifting of predicting the noise. Now, this patchify step is really the secret sauce, and it's pulled straight from the Vision Transformer playbook. You take that 32 by 32 latent space and you slice it up into a grid of little patches, just like you're cutting up a photo. So if you use a patch size of 2 by 2, for instance, your 32 by 32 grid becomes a sequence of 256 little patches, or tokens. And just like that, you've turned a spatial problem into a sequence problem, which is exactly what transformers are built for. And here's the kicker. That patch size becomes a super important knob to turn. Smaller patches? That means a longer sequence of tokens, which means more compute, more G-flops for the model to work with. Okay, so you've got your sequence of image tokens ready to go. But that's not the whole story, right? A diffusion model needs more context. It needs to know the noise time step, how noisy the input is, and if you're doing class conditional generation, it needs the class label. So the big question becomes, how do you inject this extra information into the transformer? This turned out to be a really critical design choice. So the team basically ran a bake-off between 4 different methods. The first one is super straightforward, just tack on the conditioning vectors as extra tokens at the start of your sequence. Simple enough. The second approach was to use a dedicated cross-attention block, kind of like in a classic encoder-decoder transformer, a bit more complex. The third idea was way more elegant, adaptive layer norm, or ADA-LN. Here, you use the conditioning info to control the scale and shift parameters inside the layer norm layers throughout the network. And finally, they tried a little tweak on that called ADA-LN0, which just initializes the blocks so they start out as identity functions, a neat trick to help with training deep models. And wow, the results were not subtle at all. This chart pretty much tells the whole story. We're looking at FID scores here, so lower is better. The simple in-context method, it did the worst. Cross-attention was a decent step up, but look at ADA-0. It just crushes the others. It gets an FID score that's almost half of what the in-context method got. And the best part? It's also the most compute efficient of the bunch, so you get better performance and it's cheaper. That's a textbook win-win. And this is where things get really interesting. Because this architectural choice leads us straight to what I think is the most important finding in the entire paper. It's a fundamental shift in how we should think about model complexity,
about what bigger and better actually mean. For the longest time, the whole community has been obsessed with parameter counts. It's the first thing we ask: how many billions of parameters does it have? It's been our go-to proxy for how powerful a model is. But the authors here make a really powerful argument. That's a terrible metric, especially for models like this, where the amount of actual work the model does depends so much on things like the length of the token sequence. They say, forget parameters. We should be looking at G-flops, the actual floating point operations in a forward pass. That's the real measure of complexity.
And this table just drives the point home perfectly. I mean, look at this. Compare this small DiT model with a patch size of 2 against the base model with a patch size of 4. The base model has 4 times the parameters. 130 million versus 33 million. You'd expect it to be way better, right? But look at the FID scores. They are basically identical. And the reason just jumps off the page when you look at the G-flops column. The amount of compute they do is almost the same. This is such a clear, powerful piece of evidence that it's the compute that matters, not the parameter count. It doesn't stop there. The evidence is just overwhelming. When they plot G-flops versus FID for all of their model variations, they find a correlation of negative 0.93. I mean, a correlation that strong is almost unheard of in machine learning research. It's practically a straight line. The message couldn't be clearer. If you want better image quality, just give the transformer more compute. It doesn't matter how you do it. Make it deeper, make it wider, or just feed it more tokens with smaller patches. More G-flops equals better results, period. Okay, so this is the payoff. They've got this slick new architecture, they've found the right way to condition it, and most importantly, they've uncovered this beautiful scaling law. So, how did it actually do against the reigning champs? They put their biggest model, the DXL/2, to the test on the super competitive 256 by 256 ImageNet benchmark. And it didn't just squeak by with a win. It was a total domination. It blew past all the best UNet diffusion models like ADM and latent diffusion, but maybe even more impressively, it also managed to beat the top GAN at the time, StyleGAN XL. That was a huge deal. And this was the number that did it, 2.27. That was the new state-of-the-art FID score. It was more than just a number, though. It was really a landmark moment. This was the proof that a general-purpose transformer couldn't just hang with the specialized UNet in diffusion. It could actually beat it and beat everything else, too. It was a changing of the guard. So in the end, the success of the diffusion transformer really proved that the UNet's special inductive biases weren't some kind of magic ingredient, after all. It showed once again that a simple, scalable, general-purpose transformer could come in and just win. Which really leaves you wondering, right? What's the next domino to fall? Given how incredibly well these things scale, what's the next specialized architecture that's going to be unified under the banner of the transformer?